Hey everyone, it's Dr. Calkins. Today we're going to cover experiment 19. We're in that part of the semester that's going to be full of math, so we're going to see some of that today. Title is News, Active Metal is Charged with a Salt and Battery, so it's pretty funny because we are using active metals. We're going to have salt bridges in our batteries at the end of this experiment. So this is called electrochemistry for a reason. It's because we are generating electricity by flowing electrons from and between atoms. So what we learned early in the semester is that metals lose electrons to become positive. The reason that happens is because all atoms have positive protons, and if you lose the electrons, those positive protons are still there. Oppositely, nonmetals from the other side of the periodic table, they tend to gain electrons, become negative, and again that's because if you're gaining electrons that are negative, you become negative as a result. So metals are basically giving the electrons to the nonmetals, and that usually results in them both being noble gas-like. So here's a generic example. Calcium has 2 electrons. We'd expect that it's in group 2. It gives those 2 electrons to hydrogen. Hydrogen has no electrons in this acid proton here. So by giving it 1 electron each, we make hydrogen gas. And we've seen this all semester long. All those metals that we were dropping in acids, the spectator ion was irrelevant. What was important is the metal gave electrons to the nonmetal. It became an ion that's typically soluble in solution, and then those hydrogen bubbles tend to be the result. And even we tested one with that chirp test. So as we start to think about definitions, we have to remember if this is the process of losing and gaining, we just need to better identify that. So if you're a loser of electrons, that's oxidation. And if you're oxidized, we would call you the reducing agent because you cause somebody else to be reduced. So if you're a gainer of electrons, we would say that's reduction. And if you're reduced, which is the process of reduction, then you're forcing somebody else to be oxidized, so we'd call you an oxidizing agent. So be careful here. Oxidized and oxidizing agents are opposites. Reduced and reducing agents are opposites. Think about spy movies. If you're an agent, you're usually a double agent, so when you think agent, think opposite, so oxidized and reduced. When you see agent, think opposite. Opposite, once again, oxidized and reduced there. So anytime you think agent, think opposite or you're going to get it wrong. A few cute ways to think about this that we teach you in class. These little mnemonics can be pretty helpful. One that I like is Leo the lion says grr, so Leo grr. And that stands for loss of electrons is oxidation. There's the Leo. So oftentimes we're asking for who's the Leo because we're asking for who's the loser. That's typically a metal. And who's the gainer of electrons is reduction. So again, the grr of Leo grr reminds us that whoever gains electrons is going to be reduced. Remember, the agents are opposite, so if you're reduced, you're the oxidizing agent. If you're oxidized, you're the reducing agent. You'll see that as well. Oil rig is another one that the biologists like to use. Oxidation is loss, reduction is gain. The disadvantage of this one is it's not as useful in my opinion because it doesn't remind you what you're losing or what you're gaining. So this one's a little more vague, and I prefer to use Leo grr. So what we're going to do next is talk about the oxidation rules. These rules definitely simplify our lives quite a bit, but also what's good about these rules is most of them aren't anything new. So the first rule says atoms in their elemental state is 0. Well, no doubt, because atoms in their elemental state have equal number of protons and electrons. So that's something that we saw back in maybe as early as week 2. Then we say that oxygen has an oxidation state of -2. And when we say oxidation state, it's basically like a charge. It's like the feeling of the oxygen atom, and sometimes they're being covalently bound. So charge and oxidation state are somewhat similar in the sense, so you can think of them that way and you can probably survive in Intro Chem. But oxygen likes to be -2, and that's what we've seen oxygen as a chalcogen be all semester long, since about week 2. We also go out on a limb and say hydrogen's probably a +1. Well, that's because it always gets bullied. And we've we've always said hydrogen's +1 as that acid proton, H plus in a lot of our other chapters. So we've seen this as early as week 2. We're also going to say that group 1 is +1 and group 2 is +2, but that's also what we've seen all semester long. So everything so far in these first 5 rules is really nothing new. When they say the charge of an ion is its oxidation state, they're just saying that if you're by yourself, your charge is how you feel in your oxidation state. So if sulfur is a -2 by itself, then sure, its oxidation state is -2. The next 2 aren't too bad either. They say the sum of all oxidation states, which is what we're going to practice here in a minute, should add up. And it should add up to the overall charge of the ion, or maybe just 0 if it's neutral. And lastly, we're going to say that halides usually are -1. The reason that we're now saying that most of the time they're -1 because halogens have always been -1 since about week 2. What's most important here is if you're -1, that's because you're the bully. In all these cases, that's dealing with electronegativity and that bully idea. The problem with halogens, though, is if they're with oxygen, oxygen's going to be their bully, and they're not going to be -1 anymore. So as long as they're the most electronegative atom, -1 it is, but if they're not, we're going to have to solve for them. So another way to get good at this is to practice. So we're going to do a couple of these examples, and then we'll let you try the rest. So let's look at this one. Sodium nitrite. So as we look at examples like this, we need to remember those rules at the very top of the page. So keep those handy. I'm not going to zoom out and go back and forth. I'll talk about them. But the easiest way to do this is to write it out. So just like pieces, 1 + 1 + 2. So sodium plus nitrogen plus 2 oxygens. This whole thing is neutral, so that equals 0. I'm going to put a slash in my 0 just to make sure that you don't think it's another oxygen. So now what we need is to use those rules above. So sodium is a group 1 +1, so we're going to use algebra and just plug things in, see which variables are left over. There was no rule for nitrogen, and notice it is in bold, that's the one that we're solving for. So we're just going to say plus nitrogen. This is like our x in algebra. And then we have 2 oxygens, but oxygen's really just -2 when it's the most electronegative atom, and it is. And all of that still equals 0. So what does algebra tell us to do next? Well, it tells us to combine like terms. So let's think about this number. This is 2 times a -2, so that's a -4. You had a -4 and a +1. So now we can say nitrogen plus a -3 equals 0. How do we get rid of a -3? Well, to get rid of a -3, you need to add 3, but in algebra what you learn is if you add 3 to one side, you have to add 3 to the other. These 3's will cancel, and nitrogen feels like it's +3. Has nitrogen ever felt like +3 before? No. Nitrogen should be a -3 nitride that we learned a long time ago, and we see for the very first time nitrogen is not getting what it wants. So sometimes life gives you lemons and sometimes it gives you lemonade. Here we're getting lemons because nitrogen's not going where it wants to go. In a sense, if we look at nitrogen on the periodic table, we'd expect it to go -1, -2, -3 and be like neon. Now we're seeing it go backwards, +1, +2, all the way over to +3. It's not even getting to a noble gas. Why is that? Well, you're never going to get what you want when you have 2 bullies attached. And that's the oxidation state idea. As you look at other examples, we're going to try this one. S8, that would be 8 sulfurs equals 0. We need to get rid of the 8 so we can divide 8 by both sides. Doesn't really change anything. Sulfur is 0, and that's because all things that are 0, that was rule number 1, because we're in our elemental state, no partners, no bullies, and those are always 0. So let's try one more and then we'll let you try the rest. Here we have one that's charged, that's a good example. So we're going to take chromium, there's 2 of them, so 2 chromiums plus 7 oxygens, all equals now -2 because the overall charge is -2. We're just solving for those. So 2 chromiums, there's no rule for chromium, so we're just going to write that again. We have 7 oxygens, but now we know the rule for oxygen from above. That was rule number 2. If you look at the top of your paper, you'll see it. I'm just not going to zoom out to recognize it. That's a -2, and that now equals -2 overall. Well, this is a -14. We still have 2 chromiums, and it still equals -2 overall. We need to get rid of this -14 first, so we're going to add 14 to both sides. These 14s will cancel, and this will make +12. This 14 take away 2. But we still have 2 chromiums. We need to get chromium by itself, so we divide by 2. But when you do that to one side, you have to do it to the other. These 2's cancel. 12 divided by 2 is chromium equals 6. We haven't really dealt with transition metals like that before. But if we look at the periodic table, we can recognize why. Why would chromium want to be a 6? Well, if it sits here, loses 1, 2, 3, 4, 5, before 19 is a noble gas. And that's what all things like, transition metals included. So take a few minutes to try. The rest of these, just remember the rules are at the top. All you're doing is plugging in those rules, solving. Do know that you can check your work. So even an example like this one for sodium nitrite, the easiest way to check your work is to plug those numbers back in. Just think of it in pieces. If sodium's a +1, if nitrogen we found is a +3, together that's +4. 2 oxygens is a -4. If -4 and +4 match, and we make an even, a neutral compound in this case, that's exactly what we want. So always check your work, because then you never miss it. So I'll give you a few minutes to try these, and then we'll move on to the next page. Right now, with a little practice under your belt, we're going to need that practice here in a minute. So before we get to the other type of practice of this kind of chapter with reactions, we need to recognize reactions, which is a great practice for those chapters that were so early in this exam schedule. So think about our last 2 chapters with acids and bases. Before that was balancing chemical equations and recognizing them. So just remember the combination decomposition. Those will usually do Lioger kind of electron transfer called redox reactions. Single replacement will, as long as we're picking a more active metal or active halogen. So look for something higher on that list. And this is page 125. So single replacement reactions only work when somebody is a better replacement. You don't want to marry down, so to speak. And we'll get some practice of that in lab. What's nice about double replacement reactions is they never, ever, ever undergo electron transfer. So as soon as you recognize double replacement in the homework of the lab, you can pretty much just skip it. It's not part of that chapter. That's why we focused on it so much 2 weeks ago. Combustion, though, will always undergo electron transfer because you have oxygen gas going to oxygen -2. So because of that gain of electrons, you're always going to see that there. So just watch out for combination decomposition sometimes, and it's pretty rare. Sometimes those won't do Lioger. As we look at an example, just remember that it's all about who's the loser, who's the gainer. So if these are elemental forms of phosphorus and bromine, if they start at 0, they don't end at 0 because now they're together. And normally we would think phosphorus as a -3, but notice here if bromine's the bully, you have 3 -3s, so it has to equal that +3 in order to cancel. So this is a situation where phosphorus is not getting what it wants because bromine is a bigger bully. Phosphorus electronegativity is only 2.1, bromine is 2.8, so again, that's why. So if we look at phosphorus going from 0 to positive, 0 to positive means loser. Losers are Leos. Loss of electrons is oxidation, so use that helpful hint. But again, bromine was 0 and it went to negative. The only way to go to negative is to gain. So that's the GER. The G is gain, the R is reduction. So we just need to practice. There's a practice example down here. Notice aluminum went to a +3. That's the loser. Oxygen was 0, went to -2. That's pretty common. And that's the gainer. So as we list over here, we call this combination because we only had one product. We balance the equation by bouncing back and forth. We'll get some of that practice in this chapter. And then aluminum, again being oxidized because it became positive, just like metals should. Oxygen gained electrons from aluminum. And notice one thing, aluminum has this 4 for a reason. This has to happen 4 times. Just like this has to happen 3 times to get that magic number of 12 electrons. You need as many in as you get out. So it's a two-way street. You can't have a loss without a gain and vice versa. But it's also an even street, so depending on the number of electrons that are lost and gained, there is a total that they're going to have to match up. So as we look at this first reaction, we need to be able to recognize it and balance it. So aluminum and aluminum, 3 bromines, 2 bromines. What does 2 and 3 have in common? Hopefully 6. If you have 2 aluminums over here, then you need 2 aluminums over here. That also gives you 2 times 3, which is 6. So again, we need 3 over here. We had our 6 here, and we had our 6 there. So 2 aluminums, 6 bromides, 6 bromines, 6 chlorines, 6 chlorides. Now we're balanced. It's a lot of practice and the extra credit for that as well. And then what kind of reaction? Well, doesn't have one product, so it's not combination. Doesn't have one reactant, so it's not that divorce decomposition. So marriage and divorce is out. It doesn't have oxygen, CO2, and water, so it's not combustion. Oftentimes students get stuck here. It's either double or single replacement. And notice chlorine has no partner, bromine has no partner. This would be single replacement. Now when we do these reactions, we have to worry about half reactions. Half reactions are half of what's going on. So what I like to do first is just list all the elements before and after, just like telling a story. We just need to know who's part of that story. So as we recognize this, we need to figure out where they started, where they ended. So aluminum, if we reverse these charges, it was a positive 3. And aluminum after the arrow, still a positive 3. So if you stay the same before and after, nothing happens. We saw that before with double replacement reactions. That's called a spectator ion. So aluminum is fairly pointless in this particular reaction. Chlorine was by itself. This is elemental chlorine. Our first rule on our other page was that these are 0. Bromine is by itself over here, so bromine is 0 in the end. It is true that this is a 2 and this is a 2, just like this little 2 is this little 2 and this little 2. We don't really need those. It's not going to change the answer. In Gen Chem it's very important, in Intro Chem not so much, but it's not a bad idea to put them in. Still doesn't change the fact that bromine over here was with a positive 3 aluminum, so it was a negative 1, just like we'd expect halogens to be. And for the same reason over here, chlorine was a negative 1, just like we'd expect them to be. So it's fairly easy here to see that they just changed places. We just need to think, where does the electron go in this process, because electrons in are gained and electrons out are lost. So maybe sometimes it's easy just to guess. If we put a negative here, does negative and negative make 0? Once you realize that that doesn't make any sense, negative and negative make more negative, not 0. We know the electrons go over here. How many? It's going to be 2, because there's 2 bromines going to bromine 0. Just like over here, if we were to say negative, does negative and 0 make negative? Sure. So sometimes it's easier just to plug it in and do the math first and worry about thinking, who's who in your head. Either way, we come to the conclusion that these are the answers. These are never answers, because you have to be reactants in order to lose or gain electrons. This is just the result. So don't use these in your homework, typically A, B, C, and D. Just remember over here is where we want our answers. So if we apply Leo Gur says loss of electrons, so here's our loss. So that's bromide. Loss is oxidation, so find oxidized, and when that happens, we can put in our answer, and that's bromide, not bromine, because that's a product, bromide. And for the same reason over here, this is a gain, just like this was an electron capture, this is electron gain. So gain is G, R is reduced, here's reduced, and that's chlorine. So realize that these numbers do have importance. This process here for bromine has to happen 3 times, just like with chlorine, because in total we would transfer 6 electrons back and forth. It's less important for Intro Chem, more important for Gen Chem to know that. If you can figure out who's the loser, who's the gainer, you're in pretty good shape for Intro Chem purposes. So take a little time to get through the rest of these. Just remember your first step is always going to be find your elements. So we have sodium, chlorine, oxygen. Sodium, chlorine, oxygen. Figure out where they are before, where they are after. Sometimes you have to solve. Sometimes you can split them up and think about them in your head. Otherwise, write them out. Sodium plus chlorine plus 3 oxygens equals 0, and solve just like the front page. So sometimes you have to do the front page and now this page together in order to get the answer. I will give you a hint. Out of these 6, 2 of them are all spectators. One of them very easy to recognize as a spectator, and that's because it's double replacement. So watch out for it. It'll save you some time to recognize it before. So I'll give you a few minutes to practice, and then we're going to move on to the next section. All right, so page 128, we're going to talk about our activity series. You're going to get to use this on the exam, and this is not a bad page to have available for the exam under our current conditions. But we will get a handout like this in most situations. The most important thing about this chart is it's basically our list of eligible bachelors and bachelorettes. I'm going to zoom out pretty good. It's going to be a little blurry, but what's most important is as we go up, it says loses the easiest. So if that means loses the easiest, that means lithium is by far, it's like the billionaire that everybody wants to marry. It's the easiest to lose electrons, so remember, losers is Leo. These guys are going to be easiest to oxidize. So that means way down here, these guys are the least active. Notice most of these are coinage metals because they're so unreactive, and that's a good thing. You don't want them reacting with things in your pocket. So gold, platinum, silver, some of the worst metals to have, or at least to be married to. How ironic. They're the least active, they lose electrons the easiest, least easy in this case. So if they're less likely to lose electrons, they're more likely to gain electrons, so expect these down here to be like ions. Gold plus is great at gaining electrons because it can be easily reduced. So oxidation is up and reduction is down. An important feature of this table also, and we're going to get to use this in lab here in a minute, and I don't want to go out too far, but right here, H is acid. So things above H that are more reactive and more active than acid, these are the ones that acids can eat through at room temperature. Anything down here, these are going to be safe in acid. And that's important because if you're down here, you can throw your silver jewelry or platinum jewelry or gold jewelry in super strong acids like battery acid, and they're perfectly safe. All because they're less active. They're not going to give or take electrons from hydrogen kind of idea. So use this idea here to help you. Halogens work the same way. We look at the periodic table for halogens. And we could have solved this with our single replacement reaction that we did a moment ago with bromine and chlorine. Notice activity goes up. So fluorine being the best halogen to have, iodine being the worst. So if you're married to iodine, you'd rather run off in the sunset with bromine, or chlorine, or fluorine, and so forth. Just like if you're down here, you'd like to marry up, not down. So let's prove that in lab now. All right, so here we are on page 129. We need 12 test tubes, 3 rows of 4. Basically what we have going is this chart down here. Notice on this left side, we already have it set up. We have our, from top to bottom, we need to switch these. We have our HCl, hydrochloric acid, our zinc sulfate, and then our silver nitrate, that chemical cauterizer. That's why we're wearing gloves. Also this hydrochloric acid, very strong. So here's basically H on our list, here's zinc on our list, and this is silver on our list. So these are our married couples. This one's married to silver, this one's married to zinc, this one's married to hydrogen. So kind of get a reference of those on your activity series. Up here we have the eligible bachelor, bachelorettes. So we have our copper bachelor, our magnesium bachelor, our zinc bachelor, and then some unknown that we have to kind of put in the right place of our activity series. So we have our test tube set up. We're going to go ahead and add our solutions to these 3 rows across. And then we're going to come back and drop in some bachelors and see if we can get any home wrecking to happen. So we'll come back after things are filled up. All right, so again, here's our married couples. So those are our BXs. Here's our As. Those are our bachelor, bachelorettes. These are single replacement reactions because we're trying to get, or at least trying to see if they will switch. And the way to know if they're going to switch is to look at the chart. So if you zoom into our chart here and see, and if you have both these pages open at the same time, it's a good idea. So the first thing we're going to do is have hydrogen. So if we have hydrogen, we're going to add to it copper, which is down here, zinc, and magnesium, which are both up here, and then some unknown somewhere else. So we're going to compare those observations of where they are compared to where we know everybody else is. So here's our first tube of acid. We're going to throw a little bit of copper inside. And notice nothing much, just sunk to the bottom. Here's our magnesium, so we're going to throw a little magnesium in this tube. And notice very quickly reacting. And we'd expect that because it is more active, it is higher on the list. So record those observations so far. We have zinc. I'm going to throw a couple chunks of zinc in there. And look to see for a reaction. And definitely going to town. We've seen this one a little bit earlier in this semester. And then lastly, our unknown. So this is the one that's most important. We don't need to know who it is in this lab. We just need to be able to recognize where does it belong with respect to the other ones. So nothing much yet, but you can see a few small bubbles. So maybe that means it's slightly above. So we do see small bubbles. That's enough to know that it is reacting a little bit, just not near as much as the others. So that tells us, if we look at our list, maybe we're not too far above. We definitely weren't reacting like magnesium or zinc, but maybe we're somewhere in between. So let's do another test to try. Now this time we have zinc. So here's our zinc married couple. We're going to add now copper to it. So give it a little taste of copper and see if they can do any home wrecking. These take a little bit longer, so I'm going to go ahead and add them and then come back to them. They're not as ferocious as the first one. So here's some magnesium. We have some zinc. Notice zinc and zinc, that's kind of a control. You can't replace if you're with the exact same element. Throw in some unknown. And we'll see if they're reacting yet. This one's a little bit slower sometimes, so copper, again, pretty lame, just sinks. Very low on the list, we kind of expect that. What's unique about these, here we have magnesium. Magnesium is a little bit higher, so it is starting to discolor a little bit. They're kind of getting dark, so we'll come back to those. Notice these chunks down here. These are starting to bubble even, and that's just creating steam on the surface. This one over here, zinc and zinc, we wouldn't expect anything to happen there. That's our control. And then our unknown, definitely just hanging out, doing nothing. So record those observations in that second row. Let's move on to one of our worst kind of couples of our choices. Notice over here with zinc, we were really high. Our unknown didn't react with it, so our unknown wasn't up here. Magnesium was, so it did have some reaction that would be expected because it is higher than zinc. Copper definitely much, much lower, so we'd expect it not to work, and it didn't. So we're still kind of thinking maybe it's up in that upper kind of region. So let's try some silver. So again, same idea. Let's put in a little bit of copper. Again, this one also fairly slow. So we'll go ahead and add these metals and then come back. So here's some magnesium. And And here's some zinc. And here is our unknown in our last tube. Alright, so let's check out our copper. Pretty slow, nothing much yet. Here we see it's already starting to flake apart, and that's because magnesium is so high on the list. Here, this one's already turned to a pitch black color from its silver color. And this one here, definitely doing some reaction there, so we definitely know it's above silver, starting to kind of fall apart. What we're seeing in a lot of these is silver metal starting to form. So we're going to take a minute, let these soak, and then come back and get one last set of observations. So again, let's go through these data real quick and see if there's any change. So copper just hanging out in the acid, so that was that box. Here we have metal is completely gone, so definitely reacted there. Here, metal is gone, so definitely reacted there. These are all metals that were higher than hydrogen, so that's expected. This one's still slow, but small bubbles means it's just barely above, but not enough to go too vigorously. So fill that row. Zinc's row, copper doing nothing. Magnesium, lots of bubbles, lots of discoloration, so we're starting to see some of that formation of zinc. Zinc and zinc, our control, nothing. Our unknown, nothing, so it's not above zinc. It is above hydrogen barely. Here, look at copper growing. What's so pretty about this is what we're seeing is silver metal grow on the copper. Very pretty. And even more of the same here. We're seeing all that silver metal precipitate. And this is our last row again. Here we can actually see a big blob of silver growing. And then even more so in this one, discolorized the whole thing. We're seeing lots of silver start to form. So everybody reacts with silver, so he's definitely the lowest on our list. The highest, definitely magnesium. So use your observations to fill in the rest based on what we saw. All right, we're on page 130. So electron transfer happens in batteries, so whether it's in your cell phone or flashlight, doesn't matter. Every battery has a positive and a negative. If it's the negative side of the battery, it's the side that is losing electrons that are negative. We would call that the anode of the battery. The positive side is attracting those electrons, forcing it through some kind of device. Maybe it's like a light bulb, maybe it's a phone, a laptop, who knows. But the positive side is gaining those electrons, and that's called a cathode. Cathode is a lot like cation, it's the positive side, so think of that letter T to help you out there. This is an example here of what you would see in, say, an Energizer or Duracell battery. What we're going to do is make a battery a little bit cheaper because we can make it out of pennies. So we're going to get this lab set up and we'll be right back. Alright, so in order for this battery to work, we need a after 1982 penny. The reason for that is around 1982 the price of copper got more than the actual penny value, so a lot of people started melting them. So now they put zinc inside, which is perfect for us because zinc is a more active metal. And it's a whole lot cheaper. So make sure our pennies are after 1982, so we have some of those here. So we're going to take some of these pennies. I think we're going to cheat a little bit and use more than what the lab calls for. We're probably going to use 6 or 7 pennies. And what we're going to do here is take these pennies and we're going to leave Abraham Lincoln's head alone. We're going to take away the tail side by sanding them away. So in that sanding process, back and forth, you're going to see pretty quickly that we're going to start to see some of that silvery shine from some of that zinc. So as we see that gray start to show up, we know the silver is gone, or at least the copper is gone, showing us that silver underneath zinc metal. So we're going to do that to 5 or 6 pennies, and that's going to take a while. So we'll be back after that. All right, so here's our pennies, and notice we've sanded off the back side, producing that zinc that we need in order for our battery to work. So copper on one side, and now the tail side is completely zinc. In order for a battery to work, we need a salt bridge. So here's our sodium chloride saturated salt. We're going to use these little pre-cut filter papers. We're going to toss them in, and that's going to soak them with salt so that we can have a flow of ions. The problem with zinc when it loses electrons is then it's positive. And if we don't have chloride ions to come and help, it's going to stop our battery. Also, for hydrogen atoms that are formed, we're going to need some of those sodiums to take some of their places in water. So we're going to let those soak, and then we're going to come right back. We're going to also dampen them, take them out, dampen them, and those are going to be sandwiched in between our pennies. All right, so we have our sodium chloride soaked filter papers pre-cut to size. We're going to flip one of these pennies over so that it's tails down, or zinc down in this case, and then copper up. We're going to take a filter paper and stack it over top, and then we're going to make what looks like a gigantic cheeseburger by continuing that process all the way up. So we'll come back when it's built. All right, so we have our little sandwich made. Notice it is penny paper, penny paper, penny paper all the way down, and heads on top, zinc tails on bottom, so copper on top, zinc on bottom. And now when we take this stack, as long as we're not touching the edges and short-circuiting it, there's two leads here. And what's most important is the longer of the two goes on the zinc side. So if we open these up, this longer one goes to zinc. This upper one, the shorter one, goes to copper. And notice very quickly, we have power. So you could even send some Morse code. Every time we touch that wire, we get electricity through those pennies. So if the power goes out and doesn't come back on, if you stack about 50 pennies like this, you could probably charge your cell phone. And that finishes this lab. All right, last page, and this is just busy work. So here's our penny battery in its glory. We had our zinc side of our penny, we had our salt bridge, we had the water from the solution, and then that makes zinc chloride, sodium hydroxide, and hydrogen. So notice H was a plus, now it's a 0. Zinc was a 0. Zinc was a 2+, so that gives you a little fast forward of what you're about to see as you work out the half reaction here like we did on the earlier pages, and then find out who's the Leo, who's the Gur, and so forth. As we look at the questions below, they say, why is the ion or element that is oxidized the reducing agent? We talked about that earlier. Just remember, like in those spy movies, they're opposites. So as soon as you see that word agent, think opposite. But more importantly, if you're oxidized, that's Leo. So loss of electrons is oxidation. If you're losing electrons, you're going to force somebody else to gain them. Forcing somebody else to gain them will cause reduction. The opposite is also true here. If you're reduced, if you're the Gur, gain of electrons is reduced, then you're going to force somebody else to lose their electrons, force them to be oxidized. That's the oxidizing agent, so put that into words. Number 3, one thing that we want to watch out for in the homework and now in our lab, in our early examples, double replacement reactions, those wife swap kind of reactions, those only deal with ions. And if you're swapping ions and not electrons, you don't fit in this chapter at all. So ionic reactions is another name for double replacement, and they do not do Leo-Gur redox ever. Lastly, we're going to talk about the activity series. And based on your location from our previous experiment, can you give us a guess of the region of elements in your activity series from lithium all the way down to gold? Who do you think could have been the unknown based on your observations? And then finally, what was the purpose of the salt solution in the battery? Why do we need that salt in order for it to work? So think about that question and wrap up that page, and this lab is done.